mention that the action for a particle moving non-relativistically in an electromagnetic field is quadratic in the position and velocity of the particle, and consequently the previous result, namely that the matrix elements of the time evolution operator are just an exponential of the classical action times a function of the time and the parameters, applies. Here the action is a half m q dot squared plus e a dot q dot, and I now see that I may have left out factors of c. I always said c equal to 1 in anything that I'm actually doing myself, as well as h bar equal to 1, and so putting back factors of c is a little bit hard for me. Is there an e over c here, maybe?
I think it's
E over C.
And so this then would be E over H bar C. And anyway, so if you have an electron here and a detector here, then and you have a magnetic field inside, say, a solenoid, where the current is going this way, say. Actually, I may have the current going the wrong way. No, I think I do have it going the right way. So there's an electromagnetic field pointing out due to the current winding around the solenoid. Then, but imagine this is some sort of a perfect solenoid, and you surrounded the solenoid by some mu metal which absorbs magnetic fields, blocks magnetic fields. Then what you have out here is you have the vector potential out here, but you don't have the magnetic field out there. And so what happens then is that there's a difference in the classical action of two paths, one going leaving the magnetic field, the solenoid on its left, the other one leaving the solenoid on its right. The difference of the two is equal to the integral of, well, it's also the integral of this path integrated around it, but I'm dropping that out because it's independent of the magnetic field. So the part that's just the magnetic field is an integral E over, let us say, H bar C, A dot dq. This is curl of A integrated over the surface, and that's B. So that's magnetic flux through the surface here, multiplied by E over H bar C. That's the change in the action over H bar. And so that is the change in the phase. And so what one would expect then is that if you have a detector here and then you change the magnetic flux through there, what you'll see is patterns going, the detection rate will vary as you vary the magnetic field because you'll have interference or non-interference. And that was done and measured. Some people at the time thought that it was a pretty weird effect because these people thought that E and B were meaningful and A was just some theoretical imagination gone amok and was a useless part of physics. But no kidding. But the Bohm-Aharanov effect showed that that in fact was real. Another quadratic action, of course, is the harmonic oscillator. And here, I'm going to do this quickly because I think you want to see some other things. So that's the action, and a the action of a classical path, in fact, the classical path is QC. If it goes from QA, then this is cosine omega t minus TA. These notes are, of course, online. QB minus QA cosine omega TB minus TA over 2, no 2, over sine omega TB minus TA. So that's the path, and let me just check to make sure that it's right. Clearly, when the time is TA, this is QA, this is QB minus QA, oh, I left out a term, sine omega T minus TB. T minus TA, sorry. And so when T is TA, the two signs cancel. This is 1, this is, all right, wait a second. T is equal to TA, this is QA. And then over here, we have, that's just a constant. These two can't, oh. No, this term vanishes because if T is equal to TA, you have sine of 0, so this term vanishes. If, on the other hand, T is equal to TB, then what we have is QA times a cosine, and then over here the sines cancel, and we have a QB, and then we subtract QA times the same cosine. So this satisfies the correct boundary conditions. The actual value of the classical action is m omega times QA squared plus QB squared times cosine of omega QB minus TA minus 2 QA QB. So all that's in the numerator, and then the denominator is 2 sine omega QB minus TA. So that's the classical action, and so altogether the amplitude is well, what I actually do in this particular calculation is calculate the amplitude exactly, I think I'll just let you read it. Let me just say that what happens is you have to compute a certain matrix, a determinant of a certain matrix, and I think I'll skip that, but it'll be in the online notes, and if you're mathematically inclined and want to really understand path integrals, it's worth looking at, but I don't think I should do it in class because it's fairly technical. Now, how about statistical mechanics? Well, if you have a time e to the minus I th, that's the ordinary time evolution operator. If you now let t be an imaginary time, minus I h bar theta, and of course I left out an h bar, then at this time, this thing is equal to e to the minus beta h. The h bars cancel, and the minus i's give you a minus sign. So you can go from time evolution to the Boltzmann operator, and in that way. And of course that Boltzmann operator is important because the partition function is the trace of the Boltzmann operator. say, a sum over a complete set of states of e to the minus beta h. And where beta, of course, is 1 over kt, k being Boltzmann's constant. Now one can do the same thing as we did for transition amplitudes to compute to turn them into path integrals. And the idea, once again, is to say that h, or rather beta h, which would be beta p squared over 2m plus beta v of q, I'm going to write that as n factors of beta over n p squared over 2m plus beta over n of v of q, and then I'm going to write that as epsilon k plus epsilon v. And then the Trotter product formula in this case is e to the minus beta h, then is e to the, say, oh goodness, I left out minus signs here. Okay, hold on. And so this actually is e to the minus epsilon k, e to the minus epsilon v, and then e to the minus epsilon k, and so an infinite number of factors here, e to the minus epsilon v. And so what we do is we just take two of those factors and compute the matrix element of e to the, I don't know why I left out all these minus signs. Anyway, e to the minus epsilon k, e to the minus epsilon v, qa. I guess I overused the mouse. And so this is then an integral minus infinity to plus infinity, q1 e to the minus epsilon p squared over 2m. Put in the complete set of states, the p prime states, e to the minus epsilon v of q over well, just epsilon v of q, let us say. And then qa, and then we have an integral of dp prime. And now p prime is an eigenvector of p squared, q is an eigenvector of v of q, and so this is e to the minus epsilon v of qa times an integral, and the q, p prime is a phase factor, as is p prime q, and if you put them together properly, you get e to the minus epsilon p prime squared over 2m, e to the I p prime q1 minus qa over h bar, p prime over 2 pi h bar, and this then, after a couple of steps, which I'll skip, is m over 2 pi h bar squared, epsilon to the 1/2, e to the minus epsilon, m qa dot squared over 2 plus v of qa, where I've set q1 minus qa equal to h bar epsilon qa dot. So qa dot is essentially a derivative with respect to beta. So this is Q1 at a given beta, QA at a different beta, because we're going to be effectively integrating over beta. So if you put two of these matrix elements together, what you have is, for example, Q2 e to the minus epsilon k e to the minus epsilon b squared QA is then an integral Q2 e to the minus epsilon k e to the epsilon b Q1 e to the minus, in both cases, minus epsilon k e to the minus epsilon b QA. This we just computed. This is the analogous integral, just with Q1 replaced by Q2 and QA replaced by Q1. And so this is m over 2 pi h bar squared epsilon integral e to the minus epsilon, and it's m over 2 Q1 dot squared plus b of Q1 plus m over 2 QA dot squared plus b of QA, and that's integrated dQ1 now, because we inserted another complete set of states here. Well, if you pass now from 2 to infinity in integer steps, and you here, of course, I've set Q1 dot. So just as QA dot is that, Q2 minus Q1 is h bar epsilon Q1 dot. So that's what Q1 dot means. It's given by that formula. And now if we go to n terms, what we get is QB, the endpoint, e to the minus n epsilon h QA is equal to then an integral over all these terms, QB e to the minus epsilon k minus epsilon b. This one is Q n minus 1, and then dot, dot, dot down to Q1 e to the minus epsilon k e to the minus epsilon b QA. And now we have to integrate dQ n minus 1 down to dQ1. And this is then m over 2 pi h bar squared epsilon to the n over 2. And it's an integral then of e to the minus epsilon sum j equals 0 to n minus 1 m over 2 qj dot squared plus b qj. And then the integration here is, oh, I shouldn't have done a capital. The integration is dq n minus 1 down to dq1. And now this, I'm going to set du equal to h bar epsilon, which is h bar over nkt, or h bar beta over n, or h bar over nkt. Taking the limit then, n goes to infinity, what we have is qb e to the minus beta h qa is then an integral e to the minus what's written as s sub e for Euclidean. It should be, I guess, s sub b for Boltzmann. Anyway, over h bar. Wow, I'm just wondering whether that h bar is that H bar correct? I should have just written everything with H bar, everything in natural units. And, so let's see. This was just yeah, I don't think there's no, this. Let's just look at what this is. This epsilon is beta over n. So this is just du here is, oh, if I want to put in an h bar here, then I can divide by h bar. So that's basically the idea. Whether that makes sense or not in notation is a question. In any event, if we do use this notation, and I don't think I could try to change notation on the fly, then this is the formula where S sub E of Q is an integral 0 to h bar beta of m q dot squared of u over 2 plus v of q of u du, where du is h bar beta over n. And this capital dq is nm over 2 pi h bar squared beta to the n over 2 dq n minus 1 down to dq1. Okay, so that's the path integral, and for the partition function or for the Boltzmann operator. In fact, if one writes the Boltzmann operator itself, then you have e to the minus beta b minus beta a times h is an integral qb e to the minus se of q over h bar qa. And now we've got dq, dqa, dqb. The dq has the same meaning, and actually this isn't a capital dq, these are lower dqs. So this is just the Boltzmann operator at two different betas multiplied together. Now, of course, the partition function then is trace e to the minus beta h. And so this turns out to be a rather nice path integral. It's e to the minus 1 over h bar, integral 0 to h bar beta, n q dot squared over 2 plus v of q du times dq, where dq is the same expression there. And whereas over here we were integrating over all paths that go from QA to QB, here, since we're taking the trace, we're integrating over all loops. So this is an integral over loops. In other words, QB is equal to QA. Now, in the low temperature limit, e to the minus beta h approaches e to the minus beta times the lowest eigenvalue times the lowest eigenstate of the Hamiltonian. The density operator of maximum entropy is e to the minus beta h divided by its trace, or e to the minus beta h over the partition function z of beta. And of course, I was doing these in one dimension. They immediately generalized to 3 dimensions. I think I'll skip the next section, except perhaps to just give you the result. So, for example, Q beta in 3 dimensions, e to the minus beta h QA. This is for the case of a free particle. This is mkt over 2 pi h bar squared to the 3 halves e to the minus m qb minus qa squared over 2 h bar squared beta. And in particular, the partition function, which is you set QB equal to QA and integrate over all space, what you get is mkt over 2 pi h bar squared, 3 halves volume of all space. By the way, it now occurs to me why it is that we have these h bars popping in. If we'd been doing this in natural units, of course, we wouldn't have seen the h bars, but they're actually there. And the reason they're there is, let's see, where's the first place where they come in? I think it's over here. So the way in which the h bars come in is when you have the matrix element of Q2 with Q1 and Q1 with QA. These are phase factors which, let's see, where did I do it? Yeah, you see there are phase factors, and that brings in the h bar. So the h bar comes in and really is there. And it wasn't just that I was using an overly elaborate notation. So they come in because of the matrix elements between momentum and position eigenstates. So that's the origin of these h bars. By the way, one aspect of all this is that in these integrals, these are actually convergent integrals, but the values of the momenta that are important are very high, and nonetheless the integrals converge, and it's actually correct. It's not hand-waving. Let's go to a particular case, namely high temperature, which simplifies everything. So then h bar beta is h bar over kt, and so this is short in the sense that we're thinking of the beta interval as, or h bar beta as an interval of imaginary time. This is short imaginary time because t is very high, and h bar is small for that matter. And so this gives us an approximation for this path integral and for the partition function. And this is for a more general, something more general than the free particle. So this was just a free particle. But if we're speaking more generally, then z of beta is approximately e to the minus beta v of let us say qn, the last, or it could have been q beta or qb or qa. So this qn could be qb, qa. Anyway, it's this final, these guys here. So it's that times e to the minus 1 over h bar integral 0 to h bar beta m dot squared over 2 du dq. But this thing is just very, very short, and so so what one has is one can just as well identify the q with the endpoints, the two endpoints that one integrates over. And so this then is an integral e to the minus beta v of, I'll just call it q, v of q e to the minus beta h q, which is, and here we've just gone to the free particle because we pulled out the potential, and so we can use this formula. So the formula altogether then is mkt over 2 pi h bar squared to the 3 halves. So z of beta is mkt over 2 pi h bar squared to the 3 halves times an integral e to the minus beta v of q dq, and this is just minus infinity plus infinity. So this is an approximation to a high energy approximation to the partition function, which is quite general and is actually useful. Let me also skip something here. For the case of a quadratic action, we can once again simplify things. Namely, we can imagine that we have a path that is a stationary path. So in other words, in general, we can say the Euclidean action here is the classical Euclidean action plus some detour x. And so this, it turns out, is Euclidean classical action plus a correction. And in general, that correction depends upon both the Euclidean classical action and the detour. But if the action is quadratic in the q's, then you see this thing here is this plus terms linear in x, which vanish because because this is the classical. They're detours around the classical path. So the term linear in x vanishes. What you have left is terms quadratic in x that are proportional to second derivatives of the Lagrangian with respect to the q. But if the thing is quadratic, those are just constants and don't involve q epsilon. The q don't involve the classical path. So this is the general formula. When it's quadratic, we can say that SE Euclidean classical plus x. So this is the arbitrary path, is Euclidean classical plus something that is an integral involving, well, now it's just delta E of x. There's no longer a Euclidean path in there. And the only reference to the path is the 2 times, which is to say the 2 betas. So this depends on beta, but not upon anything else. And upon the parameters of the theory, but not upon the classical path. And so consequently, what we can say is QB e to the minus beta h QA is a function of the constants. B double prime, you see, is just a constant, or a set of constants, e to the minus the Euclidean action of the Euclidean classical path. And so that's a useful approximation, and in fact in quantum field theory it's also true, and that's an interesting approximation. There's an example here, density operator for the harmonic oscillator, and that is to say the partition function for the harmonic oscillator, or the maximum entropy density operator. So I compute that, but I think we might as well just skip the details. You can read them if you want. They're online. Do you have a question?
Yeah, I was just going to ask if you could go into more detail about what you were saying about, like, if we expand this action. I can see why, like, the...
Okay, give me that again now. What?
Yeah, so whenever we expand out this action, that's the Euclidean action at the classical path plus some detour, as you were calling it. I'd say I can see we get some first term, and that the second term would be something like the variance in the action at the classical path times x. Like, I imagine we'd expand this out into something like a Taylor series, but for the fact that
you do a Taylor series. Let me do it. If I do it for the derivatives, it's sort of complicated because it's q classical plus x derivative squared. It's a little more complicated, but let's just look at v of q. V of q would be classical plus x. Okay. So this will equal v of q classical Euclidean plus v prime at q classical Euclidean times x plus v double prime q classical Euclidean times x squared over 2 plus v triple prime q classical Euclidean x cubed over 6 plus higher terms. So an infinite Taylor series.
Sure.
If it's quadratic, however, these all vanish. And this is a constant. It doesn't involve q classical because the second derivative of the quadratic function is a constant.
So you're saying if the Euclidean action is quadratic in the positions and velocities,
then you have this nice approximation. If it's not quadratic, then you still have a sort of approximation that's just a little bit more complicated. In other words, it's still true that the path integral, the total path integral, will be e to the minus se of q classical action. And at this point, I don't remember whether we have an h bar or not, but it'd be that plus then a path integral of e to the minus delta se. But now this will be q ce comma x dx. And this is an integral over all loops, but it would involve this classical Euclidean path. And you could then say, well, you could then approximate that. So this, in other words, this approximation may also be useful in the general case, but it's particularly useful in the quadratic case. And once again, the Euclidean classical solution is the one that makes the Euclidean action stationary. And I was going to skip that completely, but let me just show you what. Yeah, let me just show you a little bit what is going on here. You see, the equation for, say, a harmonic oscillator is then Q double dot is equal to omega squared Q classical Euclidean, where double dot means D2 Q classical Euclidean du squared. We're talking about U, where U is h bar epsilon. U being h bar epsilon, h bar beta. Right, h bar beta, and du is h bar beta over n, in other words, a tiny piece of that. So it's, so the dot here is du, is a time derivative, a Euclidean time derivative. And notice there's no minus sign here. The normal harmonic oscillator has a minus sign. In Euclidean space, it's a plus sign. So that's a very weird equation. But it still makes complete sense, and there's this example 20.7 for the harmonic oscillator. I use that approximation and derive the exact partition function.
I guess that's because the U is like I times time.
Yeah.
Right? And so
yeah.
If you square it, you get the minus sign there.
You get the minus sign back. Okay, so now we come to time ordering, because we don't just want to write path integrals for transition amplitudes, but especially in Euclidean, for the Euclidean case or the finite temperature case, we want to compute the mean values of operators in particular states, like the ground state, or what the mean value of an operator would be if we just assume a given density operator or a maximum entropy density operator. So first, let's flash back to ordinary quantum mechanics. Then Q of t, of course, is EVI TH over H bar, Q of 0, which I'll just write as Q, e to the minus I TH over H bar. And if we do this in Euclidean space, then Q Euclidean of U is, which is, we can think of as Q Euclidean at H bar beta. I somehow have an omega here, and boy, there are a lot of typos. This is e to the U H over H bar Q, e to the minus U H over H bar. And now the time-ordered product of T of Q1, T of Q2 is, of course, Q of T later, Q of T earlier. In the notes, I use T greater and T lesser, but it seems to me that, what do you think is most clear? Earlier, later, or older, younger, or newer, older?
Earlier, later.
Earlier, later. All right, let's go with earlier, later. And In the Euclidean case, then it's T of Q Euclidean at Q1, Q Euclidean, Q2. This is simply Q Euclidean at, well now it's greater, isn't it? U greater Q Euclidean at U lesser. That doesn't.
You could use like less than or greater than signs.
That's what I did.
Oh, that's what you did.
But it looked
okay.
kind of crazy in the notes. Because greater than and less than make weird subscripts.
Yeah.
I can do later and earlier here, but I could do bigger and smaller. I don't know, there's a notational issue here, so. And I don't know what the best notation is. I don't even know what a good notation is. Anyway, here's what is important. Let's just take B be some state. E to the minus I, TH, so I'm doing this in real time now, of Q of T1, T2, and now I'm also doing minus I, T, well, TH over H bar. A. Okay, so what is this? This is B e to the minus I T H over H bar, and then it will be Q of T later e to the minus I T, I have to do this right, it's T later minus T earlier, H over H bar, Q of T earlier, and then e to the minus I T H over H bar A, not B. So that's so it looks like that. And now, I think I've left something out here. This, oh no, it is okay. Actually, no, I screwed up. All right, hold on. I've written two equations together. And so obviously this term is absent. So it's just that. Okay. But now, if we put in we use this formula for Q later and for Q earlier, what we get is B e to the minus I T minus T later H over H bar Q e to the minus I T later minus T earlier H over H bar Q e to the minus I T plus T earlier H over H bar A. So that's the expression.
Sorry, Kevin, can I ask real quick? What is it that we're calculating here? I'm kind of confused by
We're calculating the matrix element of a time-ordered product between two states B and A and two time evolution operators.
Okay, so
it's three things.
It's not like we're time evolving the states and then calculating the expectation value.
Well, you can think of it that way if you want, but
I would just imagine they have opposite signs. Like the x, like one should be e to the I,
Oh,
one should be
what,
e
no,
to the
no,
minus
no, what, all right, let me let the cat out of the bag
I.
here.
Okay,
What we're sort of thinking about with this little t,
yeah.
this little t is going to be huge. And so we're going to be thinking about this as from minus time, going from minus infinity to some laboratory time, and then from some laboratory time up to plus infinity.
Oh,
That's what
okay.
this little t
I
is
see.
going to be. Or in Euclidean space, it'll be something different, but it has kind of that flavor. Now, we have a formula for, although I think I skipped it during the lecture, but clearly we have a formula for matrix elements of this operator, and so we also have a formula for this operator as a path integral. If we now turn all this into path integrals, what we get is an integral of b, q sub b, q of t1, yes, q of t1 in fact, q of t2, e to the I s of q over h bar, qa a dq. And this is an integral, a path integral over all paths that run from qa at minus t to qb at t. Now this simplifies if we choose as A and B eigenstates of the Hamiltonian. And in particular, if we choose them to be the same eigenstate of the Hamiltonian, say, we say A equals B equals N, and Hn is En N, then this thing over here is e to the minus 2I En t over h bar from these two factors there. And then it's the mean value of the time-ordered product at of q of t1 and q of t2 in the energy eigenstate n. And then the path integral on the right-hand side is an integral of energy eigenstate qb, q of t1, q of t2, e to the I s of q over h bar, qa n dq, and we're basically integrating over all paths that go from anywhere to anywhere because we're integrating over qa now and qb. Now this may look excessively theoretical, but it gets a little better if we look at this same expression for the case in which there's no time-ordered product at all. In that case, the equation is e to the minus 2I En over h bar is an integral of n qb e to the I q over h bar qa n dq. And so you see the phase factor is common to the two equations. And their ratio gives us the time-ordered product. So let me go to the whiteboard and maybe also erase the. Anyway, the class notes are online and are LaTeX. And on the other hand, if you want to stop me and just ask questions, I'm happy to. I don't know if we'll need both boards or not. It only takes a minute to.
Yeah, can I ask real quick, like, how did the path integral come out then? I kind of lost that. How did the path integral appear here? Like, what did you do between these two steps? You have
Or let me get
What's these steps?
yeah, I'll just point it out. I guess.
There's like
Yeah, there's like a million things cluttered. Yeah, I just don't see what happened from here to here.
resolution of the identity.
Yeah, you throw in a resolution.
Right. What we did to go from here to here is we just path integrated the whole thing. So this part here gives us a path integral over e to the I s of q from t earlier to t later.
Yeah.
This part here gives us a path integral from t later to t, and this one gives us an from t earlier. Well, it's basic. I don't quite know how to explain that. You can think of it as e to the as a path integral from 0 to t plus t earlier.
Okay.
It's anyway. It's this part. This part gives us more of this path integral, and so now this path integral goes from. It actually goes from minus t to plus t, in a sense, if we want to think of it in time. In other words, what we have basically is a time interval of length 2t. And so we can think of it as from minus t to plus t. That's the easiest way to think about it.
Yeah. So you threw in 6 resolutions of the identity or something like that?
Well, this is a time evolution. We've got 3 time evolution operators written as 3 path integrals.
Sure. I'm just, yeah, and you also have this like QB, the inner product of QB with B on the next term down.
You mean?
Sorry, no.
You mean this one?
No,
I'll jump back up and point it out. Yeah, this
yeah,
guy.
no, right there, yeah.
Yeah, this guy. So yeah, my questions are, what I don't see is first off this term. I guess you maybe inserted another resolution of the identity here. And then furthermore,
Well,
why
it's
are the key? Why are the keys?
Well, yeah, well, the way I'm thinking of it is,
Yeah.
here, let me go to the whiteboard and see if I can
Yeah.
say what one of the steps here is. In other words, so that one there is e to the minus t later h over h bar. You know one problem with earlier and later? When you write L and E, they look the same almost. All right, so what is this? We can think of this as path integral of e to the I s for this interval over h bar dq, and then it would be, all right, the way I did it there was I called this, I guess, a QB, and this one a QA or a QA prime. In other words, that's how we can write the time evolution operator. It's an integral over all final states, all initial states, outer product,
Sure.
and then this phase factor where S goes from QA at time t later. So the paths are going from QA at t later to QB at t. So that's the expression.
Okay.
And I use that a couple of times.
Mm.
And the formula, this formula written in with slightly different variables is explicitly in the notes.
Okay.
So if we then divide those two equations, we get a nice formula for the time-ordered product. And I'm a little puzzled. When did I, oh, here, it's different sides of the page. So what we've got here is time-ordered product in this, we're still in the eigenstate n of q of t1, q of t2, n is then this ratio of n qb, q of t1, q of t2, e to the I s of q over h bar QAN dq. So it's that path integral divided by a simple path integral, which is nqb, e to the I, the same q over h bar so this is the formula for the mean value in a given eigenstate of the Hamiltonian of a time-ordered product of two position operators. And if we can immediately generalize this to n position operators. So if I do that, then what we're talking about here is time-ordered product of q of t1, q of tk, say, and then over here we would have q of t1, q of tk. So that's the generalization that's in real time. Now if we do the same thing in Euclidean time, we get an analogous expression, and let me write it down. It would be n Euclidean. We're talking about Euclidean times, and now we're talking in terms of u's, u1, qe of uk, n is then again a ratio, and it's a ratio of n, let us say qb, q of u1, dot, 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 q of uk, e to the minus Euclidean action of the process over h bar, qa n dq, and it's the ratio of that to this other one, n, so it's almost the same thing, qa n e to the minus se of q over h bar dq. So this is the same thing in at finite temperature or in Euclidean space equivalently. But so if we're doing stat mech, this is an important formula. If we're doing quantum field theory, and in particular quantum chromodynamics, where the low temperature behavior of the theory, that is to say the low energy behavior of the theory, is so completely confusing because we have confined quarks and confined gluons. What one does then is look at the beta goes to infinity limit. That means that the only eigenstate that matters is 0. And so then we have the mean value in the vacuum of T of Q Euclidean U1 dot 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 Q Euclidean of UK vacuum is the same formula, but now I'm just going to use an eraser to change n to 0. And so now this thing goes to zeros. So now this is the mean value in the vacuum of a certain time-ordered product of Euclidean position operators is a ratio of path integrals. They're all Euclidean. Everything here then is real. There are no i's at all. And in fact, one can rewrite this as an integral Q of U1, Q of UK, P of U du, where P is an actual normalized probability, because P is just e to the minus SE of Q over the integral of e to the minus SE of Q dq. So let me just see, I'm also finding it right, okay, so this is right. So this is a probability, this is sort of a functional probability distribution. In other words, this is the probability for a certain set of paths, and if you integrate over that set of paths, and this Euclidean time-ordered product of these Q's is just the expected value or the mean value of these Q's in this functional probability distribution. Now, if we pass to quantum field theory, in fact, the blackboard's dry, so I can use it. Then, as you know, the way you pass from you go from there to phi I. These are equal time commutation relations, so at some x and t, pi of so if we put space-time on a lattice, then we can imagine this, that instead of a continuous variable x, we have a field at each lattice point, phi of xi, at a given time, and in fact it can be the same. This t can also be a discrete time if we want. Anyway, that will be a delta, and of course we'll have phi's commute to phi's, and phi's commute to phi's, all at equal times. So that's putting, so this is a sort of lattice regularization of the quantum field theory. And then, to make this a little more rigorous, we can say that this is phi. Let us say that A is the lattice spacing. So in other words, we have a lattice of space A, lattice spacing A, and the fields are at each of these vertices. And we can think of gauge fields as being on the links in one way or another. And then we can say that phi at position, lattice spacing A times ijk, this is a 3-vector of integers, and A is a lattice spacing. And we can imagine these are all at time 0. And then we would say pi A and LM N. No, I still have a parenthesis. And so this would be I H bar over A cubed, delta IL, delta J, M, delta Kn. So these would be our commutation relations. We would also have a complete set of eigenstates of each of these fields. So phi of A ijk will have eigenstates phi prime, and it would be phi prime A I J K. This is a comma rather than J times phi prime. Now, since the fields commute at equal times, you can have eigenstates that are simultaneous eigenstates of the field at all the lattice points. So this is an eigenstate of the field of all the field operators at all the lattice points at one time. Similarly, we can have pi of A I J K pi prime to be pi prime of A of I J K pi prime. So these are simultaneous eigenstates of pi at a given time at all points on the spatial lattice. And that's because the field commutes with itself at equal times, and the momenta at equal times, but different spaces, points, they all commute with each other. Just as in quantum mechanics we have an inner product of such eigenstates, so too here what we have is phi prime is a product over all points in the spatial lattice, a square root of A cubed over 2 pi h bar e to the I A cubed phi prime of A I J K pi prime A I J K over h bar. So it's a product of all these space factors. And if we think in terms of, if we imagine that the lattice space goes to 0, then in that limit we recover a continuum theory in which there are eigenstates of the field operator at x and time t, and they are phi prime of x, phi prime, and then there are eigenstates of the momentum operator at a given time that are pi prime of x, Now, these eigenstates of the field operator and the momentum operator at a given time, these are like the Q and P eigenstates that we start with in quantum mechanics. And these are states of infinite energy. So these are very unphysical. These are mathematical states as opposed to physical states because they have infinite energy. Many people forget this and imagine that these are just ordinary states. We can, on the other hand, talk about coherent states, and then the coherent states would be eigenstates of the positive frequency parts of phi and pi. And those, of course, have finite energy and are physical states. All right, we're sort of basically out of time, so let me just sort of stop here. The plan is to go just a little bit further with this and then talk about perturbation theory in terms of path integrals, then quantum electrodynamics in terms of path integrals, but just basically setting up the path integrals, not actually using it. And then fermionic path integrals in terms of Grassmann variables. I think that's worth seeing because it's so different from what we're used to. And if supersymmetry turns out to be a symmetry of nature as opposed to symmetry of theoretical physicists, then it'll become really important. So it's, on the other hand, it's amusing mathematics. In fact, it just amazes me all the time that it means anything at all. All right, I guess we can stop now.